Welcome, everyone. You're tuned in to the Boise State Physics First Friday Astronomy. My name is Brian Jackson. I'm a professor here in the physics department at Boise State. I teach astronomy and physics. We're really glad you could join us this evening. We're really excited to have a very interesting talk for this evening, and I'll get to that in a second. For those of you who have never attended a First Friday Astronomy talk, welcome. These events take place on the first Friday of every month. And so if it's a Friday, the first of the month, and you're looking for something to do at 7:30, this is the place to come. We've started a new YouTube channel that you can easily find by going to boi.st/astrobroncoslive. And I'll put that in the chat window here, boi.st/astrobroncoslive. And so we'll post all of the videos. They've been posted previously on my website. We're going to post them as well on the YouTube channel. So that's a good place to catch things. We also have a Twitter account now. It's Astro Broncos. So if you're on Twitter, go follow us on Astro Broncos. And so you'll see a lot of information coming out through those channels from now on. These First Friday events have a partner event called the Third Thursday event. And those take place on the third Thursday of every month. What we do there is we get some practice doing virtual stargazing. We answer astronomy questions. For those events, those are held over Zoom, and so we ask that people register for that. And that's you want to register for that at boi.st/third Thursday, and that'll also put in the chat window. For our First Friday events, these are live streamed, as you can tell, and we invite our guests to submit questions to our speaker through the chat window. And if you're on YouTube right now, you're probably seeing me enter things in the chat window. So as you're watching the talk, if you think of interesting questions to ask, Heidi and I will both be paying attention to the chat window, and you can just post your questions in the chat, and we'll make sure to have them asked by the end of the talk. Okay, I think that's everything. So this evening, we're very fortunate to have Dr. Travis Longcore. Dr. Longcore earned his Bachelor of Arts degree in geography from the University of Delaware, and then a PhD in geography from UCLA, where he won a National Science Foundation Graduate Research Fellowship. And so for those of you who are in the know, you know that those NSF Graduate Research Fellowships are quite prestigious. Dr. Longcore was previously an assistant professor at the University of Southern California before joining the faculty at UCLA. He's currently in the Institute of Environmental Science. Please correct me if I'm wrong, Travis. I think I might have said that incorrectly.
Environment and Sustainability.
Environment and Sustainability, excuse me. He is a world expert on light pollution. And so I think we're going to have some very interesting information tonight on light pollution, and he's also done work here in Idaho, so hopefully we'll hear a little bit about light pollution here in Idaho. And with that, I'm going to stop talking and turn it over to Dr. Longcore.
I hope you want to hear a lot about light pollution in Idaho. So someone will make me co-host here as we get started. Thank you, Brian and Heidi, for hosting and inviting me, and having a well-rounded set of speakers. If you'd told me when I was getting my bachelor's that I would someday give a lecture in a physics department as a guest speaker, I would have laughed at you. But careers go in interesting directions. And so here we are. I'm going to share some slides here to get us going. And there, because we're going to talk about light pollution and the Central Idaho Dark Sky Reserve. As I said, my name is Travis Longcore. I'm at the UCLA Institute of the Environment and Sustainability. And I have to say at the outset here, this is not just my talk. This is work that's been being done what has happened here? All right, this work has been done by a group of students in a senior practicum in environmental science at UCLA. It's a model by which we take on clients from off campus, and then students do research over the course of basically an entire year. They do lit reviews and whatnot. In the first quarter, we're on a quarter system, and in the second 2 quarters, they really dig in with an advisor, and that's been me, on a particular thing. And our client has been the Central Idaho Dark Sky Reserve, in particular represented by Dr. Stephen Pauly, who was instrumental in getting that reserve established. And so the work that you're going to see today, the numbers, the models, etc., is all work that's been developed by Maria, Sean, Jacob, Megan, Yeva, Lynn, Cassidy, and Jacqueline. We're kind of 2/3 of the way through the project right now. And they just last week gave their preliminary results presentation to the class. And so I'm drawing on that and augmenting it a little bit here for this presentation. And I want to thank you for inviting me. I'm glad to be here, and welcome also the folks out there from Twitter and Facebook and whatnot who saw something interesting come across the wire and decided to pop in and join us. So this is the Central Idaho Dark Sky Reserve, the photograph by Niels Reby, who's also very active at the reserve, sort of demonstrating why it is that this is a place that people treasure. The ability to get out and see the night sky, to see the Milky Way with the naked eye. And it becomes ever more interesting and important if you compare it with some of the places there where folks live in this country, like, let's say, Los Angeles, where I am today. You recognize how special this really is. And those of you in physics and astronomy probably don't need any definition of light pollution and its levels, but I decided to make one up for Idaho anyway, just for outreach and communication's sake. And excellent, this is on a Bortle scale. Excellent dark sky site to Los Angeles. And so Los Angeles on the Bortle scale, which is based on the number of stars that you could see, is basically a 9. Downtown, I'm maybe where I am in the hills a little bit, maybe between an 8 and a 9, but it's pretty bright and you can't see very many stars. And then we go down, the nearest sort of 8, 9 to you in Boise would be Denver. A 7 would be Salt Lake City. Boise is about a 6, right in the middle of Boise. Kuna, which I only know from the map, but I looked and tried to figure out the closest place to Boise with a 6 sky is Kuna. And then Haley and Ketchum, which are in the reserve of the buffer area of the Central Idaho Dark Sky Reserve, are right there at a 4. Garden Valley, if that's familiar to you, is a 3. Stanley, which is actually within sort of the closest one to the core of the reserve, is a 2, and the reserve itself is a 1. It is an excellent dark sky site. And so what we're talking about here is the difference between looking up and seeing something like this. As you look up from a campsite. This happens to be taken by a former student of mine on the north rim of the Grand Canyon. There's a campfire here and just a slight bit of light pollution there on the horizon. But to be able to see this versus when we do this kind of work and take a picture of the full sky in Los Angeles, you get something like that. And of course, that's with some clouds. And usually astronomers just stay in when there's clouds, but because we care about conditions all hours of the day when we work on ecology, we've gone out and we've sampled and measured light pollution under cloudy skies in Los Angeles. And this is what you get. And it's basically almost twice the illumination of the full moon during a night with no moon at all. So that's the sort of what's at stake here and the difference on the landscape between a place that's got this natural attribute that's still intact versus where we have millions and millions of people living around the globe and what they're missing by not being able to see that. So how did I get into this? Well, I'm a biogeographer. I work on nature in cities. And over 20 some years ago, my then girlfriend, now wife, and I got interested in thinking about what happens to the sort of half of life that is nocturnal under light pollution. And what kind of impact might that have? What does it do to species that rely and have relied for all of evolutionary history on there being these natural patterns of light and dark, lunar patterns, daily patterns, etc. And so we were coming at it from a biogeography perspective. We did some work. We put together a conference in 2002 that got covered here in Science News, Blinded by the Light, Does Artificial Light Disrupt Ecosystems? And it was held with our nonprofit and at UCLA. It was called Ecological Consequences of Artificial Night Lighting. And we did that because we'd been asked by some people from the dark sky community, astronomer, amateur observers, et cetera, said, and the International Dark Sky Association, they'd asked us, can you put together a white paper on these impacts on wildlife? We thought, well, we can't really do anything more than what's been done already, because there'd been a few white papers here and there in Germany and in the UK. But we said we can get everybody together and have a conference and talk about it. So we did that, and it kind of sort of got things going. Around that same time, the National Park Service was starting and pioneering its use of all sky photometry to measure light inside of parks. And so this was actually a Science News article from 2004 about that program. And so out of this work came a paper that we wrote in 2004 called Ecological Light Pollution, which we really kind of tried to distinguish between affecting ecosystems and ecology with lights and affecting the view of the night sky. So we talked about ecological light pollution versus astronomical light pollution. And it wasn't because we thought that astronomical light pollution wasn't important. We knew that it was. We just needed ecologists at that time to sort of get together and start looking at this as a real thing. And to take it seriously and bring together all of the work that was sort of scattered here and there throughout the literature into one place. And so out of that conference that I described, and this chapter, this paper on the left turned into the first chapter in that book on the right, which came out in 2006, called Ecological Consequences of Artificial Night Lighting. And we really intended it as to sort of let people understand that this was a real thing that deserved attention. There were things that people knew already quite well, like sea turtles are attracted to lights on beaches. Insects are attracted to light. People have always known that. Birds are attracted to light during migration. All of those things end up with basically dead bodies on the ground. But there's more subtle things that go on and more pervasive things and multi-level ecological relationships to be had. So we did the book, got that together, and now fast forward 15 years and you've got these now coverage in, Science, Nature, the scientists talking about major experimental work that's going on, because ecology and ecological research has really taken up the night lighting, light pollution theme and run with it, especially over the last 15 years. So that's kind of how this has built out. And now we can look around and start to see some themes that have emerged on the key things that are effects on wildlife. And I put them, just for sake of communication and argument, in sort of 4 big bins. One of them is attraction disorientation. Those are ones that have probably been familiar for a long time, about organisms that are orienting in the world, and lights affect that. Connectivity is where it's maybe a special case of orientation and attraction, but it's where animals find their landscape severed by lights, that they don't want to go into a lighted zone and therefore miss that movement across the landscape. Then there's sort of interference with pollination and foraging, but sort of all these ecological interactions, insects and plants, insects and other insects, birds and insects, cougars and mule deer. All of these things are affected by lights. And then the last category is circadian rhythm disruption. And this goes into all of the physiological consequences from exposure to light at night. We know, going all the way back to the 1920s, that you could induce birds to lay eggs at the wrong time of the year by exposing them to artificial light at night. And there's a whole suite of these things. And this is also where this field sort of intersects with the whole realm of human health and the effects on human health of circadian disruption that arises from a lifestyle of living under electric lights. So just to give you some examples of what these things look like. So attraction and disorientation. This is actually a photograph from some field work that colleagues of mine at the Smithsonian did for a site down in the Peruvian Amazon. And that light is a site that's out in the where there's going to be basically an energy facility installed. It's going to happen, so there's nothing that we can do about it. And the question that we had gotten and that I consulted with and collaborated with the Smithsonian, they had been asked and I collaborated with them, was how do we minimize insect attraction? So this is from that study site, and we actually use spectrum to try to reduce the attraction of insects. But this sort of shows just how much biodiversity out there and what happens when you put light out into a naive habitat that sort of has its full complement of biodiversity. So sort of an extreme thing, but we could show other things. We could show a picture of a lighthouse from the 1890s or the 1910s and show birds that were attracted in equal abundance to these insects, to this light. So that's an example there. Here's an example of how circadian rhythms and also daily and annual rhythms are affected. This is a soybean field from Nebraska. I got this from Nebraska Extension. They sent it to me because I'd seen it, and it's a really great example. At this time of year, the soybeans should be brown, like the ones on the right-hand side of that field. But you see how there's sort of scalloped shape of green going across there, and that corresponds to the light poles along that road. That's because these are cold season soybeans, and they set seed when they detect that the days are getting short. And there's this threshold there. And if they don't think the days are getting short enough, they don't set seed. So all those green soybeans, instead of setting seed, they're just going to die by being frozen. And that's lost crop to the farmer here. They want them to look like it is on the right because it's gone through its process. The day's gotten short enough, set seed, then you can harvest. So this is actually a significant issue for farmers, not this farmer in particular, because as I got the permissions on this image, I learned that this particular field has now been turned into a Walmart. So there's no more soybeans there, which isn't necessarily the way we want to solve these problems, but is sort of an illustration of that interface. So pollination. Oh, and this is a photograph from Florida. Ward, and I wrote it down. I'm sorry, I should have remembered his last name. Not my photograph, but pollination by a nocturnal moth. Most moths are nocturnal, just showing this sort of delicate relationship between plants and their pollinators. And this is the kind of thing that's very easily disrupted. And there's been a slew of papers in the last 3-4 years showing just how easily it is to reduce the amount of seed that is set by adding lights, to also have spillover impacts from the nighttime to the daytime by affecting the pollinator community. So a study showing out of Switzerland, incredible study showing that lights at night affected the nocturnal pollinators, that resulted in less seed set, and then it was a spillover effect because there was fewer flowers on the pollinators during the daytime. So there was actually, by adding a street light over this experimental site, you ended up with a lower pollination and seed set during the day for day pollinated species as well as the night pollinated. It's pretty incredible stuff. And then of course, movement across the landscape. And this is one of our local celebrities in Los Angeles. This is P22. P stands for Puma. And I know you've got enough that you don't give them names up there in Idaho, but when one lives in Griffith Park, right outside of downtown Los Angeles, he gets to be pretty famous. And so I got to thinking about this, and you look at this animal and the eyes there, look at the size of those eyes, and think about the visual system, what this animal can do as a nocturnal active species. And so we tried to sort of imagine what it might be to be in Griffith Park at night and look out at the landscape. And this is a hemispherical image, so we're getting a whole half of the environment at one time. We're up here in the hills. That's Los Angeles down there. There's some sky tracker lights there, maybe from a premiere or something in Hollywood. This was pre-COVID, and this is what it might look like to you or I, and it's pretty bright to you or me. But imagine you had a visual system that was 10, 20, 30, 100 times more sensitive than we have as humans, and that there's not just sort of light and dark is but gradations. And so imagine your visual system is better, or even better still, or imagine that, you know, you're like that mountain lion. You're probably able to see the light, the environment with that level of specificity, with those big eyes that he's got. And what that means is that they're adapted to and can use this environment, but also just how bright the night looks to them, the way that we have lit it up. And I think that's really important as we start to think about it, that there's these orders of magnitude difference in the way other species perceive brightness. And so something that may look dim or dark to us may be perfectly and sufficient illumination to some other species, and things that are even mildly bright to us may look like just a big old mass of molten lava that they'd never want to go near. And you can sort of start understanding then how you could use light pollution to understand how animals move across the landscape. This happens to be Los Angeles at a little bit of an angle. Griffith Park over here is where P22 is, that mountain lion. And this image in the background is actually a color enhanced version of light pollution. It came from a small sat, a little bread box sized satellite that a colleague of mine at Aerospace Corporation sent up, and specifically to test out higher resolution light pollution measurements. And we brought it in and we said, here are some areas where those mountain lion might go. And we created what we called a darkest path analysis. Where would be the darkest route across the landscape that was also the shortest route? So it's sort of the cumulative short and dark route. And what it does is it identifies a couple of key locations. One, it sort of exactly predicts the two places that you might be able to get over a freeway that runs right through here. I'm assuming you all can see my mouse. It also predicts two places, and in fact, a location to get over a freeway that goes right across here that now has been targeted for an overpass because no mountain lions go there because there's a freeway there and it's really bright. But it does identify the possibilities for moving across the landscape and illustrate how lights and linear structures that are lit brightly at night can affect movement. Another classic example of this, of course, would be migration of birds at night, going from Central America or the Caribbean up to Canada to breed, and running into cities along the way, being attracted to those lights and them acting as a barrier. And we lose, you know, hundreds of thousands and millions, in fact, of migratory birds each year to obstructions along their migratory routes. So light as a barrier. So I mentioned all that as sort of a background for how I got into this as a field and some of the things we're looking at from the nature section. And then it's such a pleasure then to turn around and work at a place, if remotely in my case so far, like the Central Idaho Dark Sky Reserve. So dark sky reserves are certified by the International Dark Sky Association. It's the sort of highest classification of places. They consist of a core area and a buffer area. There's two core areas in the central Idaho. So here's Sun Valley and Ketchum down here, Stanley up here, Boise County, and then Ada County and Boise here over farther to the west. And so this was brought into being through a lot of people working. I can name a few names like Dr. Steve Pauly, Carol Cole, Steve Bote, and Stanley, and there are many others who worked very hard with the International Dark Sky Association to create and recognize this as a reserve. It happened in 2018, I think it was finalized. There's only one other one in North America, which is the one around Mount Magentic in Sherbrooke, Quebec. Right. And so this is a significant, important dark sky location, had to meet criteria to be declared. And one of the things that they need to do to retain their certification over time is to track light pollution and progress and in ensuring that risks are abated and that basically that things don't get worse and degrade that environment. And so they are then the client for this practicum group. And I'll say, when I say that the students did everything, like this is student work you're looking at right now, just starting from the maps on through. So the project that we took on has three big pieces that I want to talk to you about today. One is assessing the status of trends of light pollution in and around Central Idaho Dark Sky Reserve. Second is to evaluate the influence of policies on the light pollution trend. So there are a number of policies that have been in place either before the reserve was established, or have gone in place since then, or have been updated, and we're very curious to see what effect that might have on trends, and then develop some approaches to promote astrotourism and education in the Central Idaho Dark Sky Reserve, because part of the purpose of all of this is, in fact, to harness this resource of the way nature is naturally, right? To harness that as a means to educate people about light pollution, the importance of protecting dark skies, and of course, astronomical observation that goes along with it, and the protection of ecosystems that goes along with it, and also to give the communities in the reserve a payback on that shepherding and stewarding that resource, right, in a way that allows them to invest in and reinforces a community ethos of protecting the night sky. So those are the three things that I'll talk a little bit about here in the second half. So how do we do this? So here, the data that we have two ways. One is looking at data from the sky, and the other is looking at data from the ground. And given the year, we didn't get a whole lot of data from the ground. In fact, it was a few of the students themselves who decided that they were going to take their own time and go to the reserve on their spring break as individuals, not as an official trip, and go ahead and try to grab a little data from the ground that I'm going to show you. But the big tool we have is remote sensing. And if you've ever seen this image here from NASA, they call this the black marble or whatnot. This is from the Suomi VIIRS, which is Visible Imaging Infrared Radiometer Suite, or I always forget the acronym totally, but it's the day-night band that we're interested in, the DNB. And it goes over every night and measures lights coming up. So it's measuring upward radiance. It can be moonlight that's shining on the top of clouds, but if it's new moon and there's no or low moon situation, then, and there's no clouds, then we get the light from human activities, fires, etc. There's a whole series of procedures that are pre-processing that's done. Now it's done at Colorado College of the Mines by Chris Elvidge's group there. And it processes these data, creates monthly composites, annual composites, takes out transient lights. So you can literally watch the lights go out after a hurricane with these data. If you know where to pull them up the next day, you can watch fires in these data, but they take all that sort of stuff out and create a stable lights composite for monthly and annually. And so the VIIRS data extend, basically calibrated VIIRS goes from about 2013 to present. Before that, there was another nightlight tool, which is the Defense Meteorological Satellite Program. But it was a lower resolution, wasn't designed explicitly for this purpose, but we used it for a long time. And I'll show you a little bit of that just for context. But because we're interested in helping the reserve track from year to year, this is the best data set we have. And so we wanted to go back and do this a little bit. So we download and project out each month and the process data consisted of 2013 to 2019. So we had 84 months of data. We took a 300 kilometer buffer around the reserve. That circle isn't exactly 300 kilometers, but that's what we did. And then 450 individual geographies, meaning different units in which we would look at the trends in light pollution, because policy happens at political scales. So we looked at all the counties, we looked at all the cities, we looked at all the parks, we looked at the reserve itself, et cetera. And so that led up to something on the order of 37,000 points of data to graph out and explore and figure out what was going on. So there's some limitations to this. First, that full monthly data are available only for 2013 to 2019. So in another year or another 6 months, we'll probably be able to add 2020 to this. And then a little later, we can add 21. Upward radiance, the light that you see from a satellite, varies widely in the wintertime because of snow. And so when you look at the data, it's very cyclical and it gets very bright in the wintertime, and it varies based on how much snow there is and, frankly, how dirty it is. And so that raises some questions about how to analyze. There's also some issues with getting full data in the summertime because the overflight doesn't always come after the end of astronomical twilight. And consequently, there are some months missing at northern latitudes, such as yours, in the summertime. So what I'm going to show you are April, August, September, and October data. And I have them all, and if, depending on how much time and how interested in getting into the weeds anybody is, we can look at them. I actually coded up a viewer so that we can go through and show you the raw data. But this is a 4-month periods. And then there's another little issue. And you can see I've got a red line and a blue line. So this is the Central Idaho Dark Sky Reserve. I'm doing summed radiance here. So this is like the total nanowatts per square centimeter per steradian. So it's a radiance measurement of lights up as seen by the satellite, summed over the entire reserve. So these numbers are going to vary based on the size of the area that we're looking at. And I do that because small towns are going to have much smaller numbers. Larger areas are going to have larger numbers. So you can sort of understand the magnitude of the light that might be affecting observation at any point inside the reserve. And so what we see here, we have 2000 to 2019, and then we have this piece here over, it says air glow included, no or yes. And this was one of these sort of methodological questions that we had to kind of grapple with, and the students had a little fun thinking about. The processing of the VIIRS data changed in 2017. And in 2007, before 2017, they calibrated the data to take out air glow so that the light that you're seeing is basically artificial light as you look down. After 2017, they stopped taking out air glow. So especially if you're looking at a dark region, if you go pre-2017, you can get very close to zero numbers that are very close to zero. In fact, you see I've got a minus 1,000 here to include this, the band of the regression line. It's not really a negative number, but it's very low. Whereas after 2017, you can see it jumps up. And so we decided that since the data in the future are all going to be with the air glow included, that we wouldn't bother trying to adjust one or the other. We just set it up this way and say, going forward, it's going to be continuing on this trend, but we're interested in what was happening up to 2017. It's also very convenient that that's when the reserve was established. But so this is a methodological issue that you come across as a processing issue. People have created adjustments that would move this line down, and you'd be able to track the trend. But that would add another step for the next group that wants to repeat this methodology. And it would be going back to the old methodology. So we decided to just leave it as a split here. And so this, even though it looks like there's a big jump, we know that jump is because of the change in adding the air glow back in, or not taking it out in the first place, actually. And we have basically two non-significant curves that are both negative. And I will take that as, if I'm the Central Idaho Dark Sky Reserve, that's a good thing. Right, that means I would be, neither of these are significant. They don't explain a whole bunch of the variance, but even if you line the two up and it were even borderline significant, that would be good, right? It would be less light coming up from inside the whole reserve. So that's the core areas and their buffer altogether. So then we start looking around. Here's 300-kilometer buffer from it. Basically the same thing. Not a whole lot of explanatory value, and the R-squareds are all down around 0.1. They're both non-significant. If you added them up, maybe there's a significant decrease. We don't know. But again, this is, from a statistical perspective, this is flat. That's good. We'll take it. And we're happy to be able to show that we can do this, because now the reserve can go back every year and make sure that they're staying on these trends. We got the baseline. Now here's then is something else. There's a mine. that is just a little bit north, about 40 kilometers north of the middle of the preserve, called the Thompson Creek Mine. And this is interesting. Right? You can see that there's a significant decrease, R squared of 0.52. We got a highly significant p-value. After 2017, there's basically no differences. And we were looking for this, and we're happy to see it because we know what happened here is that they had to do outreach to this mine before the reserve was established. So they went out to the mine, they talked to the folks at the mine, they say, hey, we're setting up this reserve. Can you please figure out some ways to reduce the amount of light that's coming out of your operations? And they did, and it shows up on the satellite. And even here, this is basically a flat line. So the offset here is attributable to the air glow. And, the maximum, if we were looking at all the data, the maximum, in December 2019 was a little higher than the maximum the year before, but not enough to worry about yet. And it's really a great indicator, a quantification that can be continued from year to year to track this source and also show what friendly talking can do to solve some of these issues, to make sure that you preserve this resource for astronomical observation and ecology. Here's the city of Boise, and this was interesting to me, that the post-2017 numbers, it's not significant. There's too much spread in there to say that's a real trend. But no matter how I look at these data, both these lines look like they're going down a little bit. And I'd be happy about that. There is a transition that's coming up. Either it's happening now or just got started in the last year to LEDs as the street lighting in the city of Boise. And depending on how it goes, that can make things considerably better, or it could make things worse. And one of the problems with the current satellite, now here's welcome to things remote sensing people worry about, is the satellite only sees wavelengths from 500 nanometers up through the visual spectrum, which means it doesn't see in the blue. And the blue is where the peak emissions of sort of full spectrum white LEDs occurs. And so it may be, if there's some conversion going on here where there's better shielding but more blue, you could have an apparent decline in the upward radiance while there's not a real decline because the blue isn't being detected. So it's basically blue blind, this satellite. Now, why they did that, everybody who does light pollution work wish they didn't, but they did. And we're all, proposing various ways and instruments and workarounds to try to get the full picture. So again, nothing significant, suggestive, very curious, because Boise does represent a lot of summed radiance as you look at it together. Here's Haley inside the reserve. That's pretty much a flat line. Here's Ketchum inside the reserve. Interesting, was headed down before, headed down after. Is it significant? Maybe it is, maybe it isn't. Interesting thing to know, there was a policy in place since 2013. So this was under a policy that should have been upgrading lights and getting them more into compliance over time. And there was an update to that policy in 2017 that made it more strict. And so as time goes on, we'd like to see and confirm that this is a real trend and that it actually continues. Here's McCall, looks like a little, decrease and then a flat line. Here's Stanley inside the reserve. That one looks significant. And that was absent policy, but with a very active city council and mayor interested in and bought into supporting the dark sky reserve. And they have also put a new policy in place that time will tell if that actually reduces light pollution as well. So that's an interesting one leading up to that certification, and then, awareness, getting people to recognize that lights that are directed upward or some portion upward aren't actually benefiting them for the tasks here on the ground. And they have now I just learned this from my students the other day. They're now replacing their street lights with a lower color temperature, meaning there will be less blue in them, which means the light scatters less. And it's a physics department. I don't have to explain it like I usually do. Here's Bellevue. That's not anything, I don't think. We'll see, time will tell. But there's no policies in place there. And there's enough slop here that I'm uncomfortable setting it. Policy only gets added in 2019. So we don't know what's going to happen from that yet. Here's Sun Valley itself. That looks reasonable, but again, no statistical confidence, especially given some of these outlier years. And now to look back historically, because all that's post 2013. There's another set of satellites I mentioned before, the Defense Meteorological Satellite Program, DMSP. And here's the city of Boise, and I grabbed this quickly off a site. And any of you interested in this can do the same. It's called lighttrends.lightpollutionmap.info. Both www.lightpollutionmap.info and lighttrends.lightpollutionmap.info. Incredibly important resources for people looking at dark skies, places to go observing. This is all the data, the annual composites from the DMSP. And you can see there is, in fact, a linear, more or less, big spread, but an increase from the 90s through 2013. And so now we're sort of maybe stabilized at this point, and we'll see, depending on the changes that happen, depending on the level of population growth and development, et cetera, we'll see how this happens in the future. But just to put in context, this period 2013 to 2019 that we're looking at often comes at the end of a period of increase, right? And that is something to worry about. So that's all the satellite piece. And there's another piece. We have a piece of equipment called the Sky Quality Camera. This is one of my former students actually taking a picture on a beach in Los Angeles. That's the Santa Monica Pier, if anybody's ever been to LA. It's a digital camera with a hemispherical lens. You point it straight up, and then you take an image long enough for it to get enough photons into the camera to make an image. So here in LA, that might be 10 seconds at night or 15 seconds. And out in the reserve, it's 2 minutes. So this is sort of an average sky. This is out in the hills to the west of here in Los Angeles, sort of showing what those kind of images look like. It's enough to see, we can see the Milky Way, but we can also see, various pieces of Los Angeles all around on the horizon. That can be then turned into quantitative data. And this is a product called Sky Quality Camera. It's programmed by a team in Slovenia, led by Andre Mohar, a company called Euromix. And they calibrate the lens and the camera together in the field. So all these cameras that we use, we send them to Slovenia, they send them back. And the lens and the body are paired. And then because we can then calibrate it, you know all about the vignetting of the lens, you know about the sensitivity of the camera, and it goes through and there's a calibration file and then it gets analyzed. So we have on the left the sky brightness in visual magnitudes per arc second squared, or you can set it to luminance in terms of whatever it is, candela per meter squared. And on the right-hand side, you can extract the correlated color temperature. And those two things can tell us quite a bit about what's going on with the light pollution. And there's a bunch of summary statistics here that we can get into later. So this, though, in comparison, is the image that my students on their own time during spring break in the middle, it's basically 4 in the morning in March in the middle of central Idaho. This is the image that they got. It was 4 in the morning because you have to do this when the moon is not above the horizon or there's a new moon. And the time that they were able to be there, it was a period when there was just a little window, like a 40-minute window after the moon went down and before the astronomical twilight started to dawn. And so this is 4th of July Creek in the middle of the reserve in the wintertime. You can see there's some low clouds. They almost didn't get a clear sky at all, but it cleared up for them at the last minute. So that's our image. We can project it outward. to start to understand it a little bit. So the up is the top of the sky is still here instead of in the middle. You're looking due south. North is both on the left and the right. If you can imagine, this wraps around entirely. And then we've put in a bunch of different potential light pollution sources. Boise is here 118 kilometers away in the southwest. Thompson Creek Mine is here about 35 degrees or 45 degrees in the northeast. But you can't really see too much in the raw things. You got to process it through. And here is the luminance. So this is in microcandela per meter squared. And you can, this is a dark site, I got to tell you. You know, this is nothing like what I deal with in California. It's rather quite incredible. But you can just barely see these sort of lighter blues on the horizon here, right? Here, 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 a little bit there. And that's for real. This is Ketchum, Haley, Bellevue to the south. The Thompson Creek mine has to be hitting some low clouds here and sort of scattering out through there. But it becomes much more visible if we look at the color temperature instead, because these lighting sources all have lower color temperatures than deep space. And so if you look at the yellows here, which get us down 36, 3000, something like that, sort of composite color temperature, you can now see that there's much more sort of lower color temperature light in the horizon here and around this direction than there is over here. Right? So there's basically nothing within any distance that could affect your sky looking to the northwest from the middle of that site. And the things, and Stanley happens to be behind a tree. And that would just be a tiny little globe there. Maybe that little piece there is a bit of Stanley. So this is our way to connect up those remote sensing data, because the way we figure out the distance and where the light dome of the cities are is putting this on a map with the remote sensing data and figuring out the angles and then translating it back here. And then we can summarize and we can see, you know, this is sort of the total view here. It's an incredibly great site. It's got a sky brightness approaching 22, which is incredible. It has just a little bit of these lights down on the horizon. And in fact here, because there's some clouds, we have a -5 sky brightness index, meaning it's actually darker than a natural sky. And that's because there is some sort of high thin clouds here that's filtering things out. And then on the horizon, I can't see the number behind here, but maybe we're 40% higher than a natural dark sky as you get down on the horizon here, compared to, you know, Los Angeles, where that number gets into the thousands of percent of unnatural brightness. So we'd love to do more of these, but this is what the students were able to get just through this one trip in March. And then the other part of this is the astrotourism bit, which is trying to understand where and how people would want to use this, and what can you promote in terms of people visiting. And again, complete credit to my students here. They're tracking down a paper on astrotourism that was done for Europe, sort of a concept paper, and they turned it into a spatial model. And basically saying, if you're a tourist, you probably want to be close to food and lodging, close to campsites, low artificial night sky brightness, so dark skies. And for this, we used the World Atlas of Artificial Night Sky Brightness, which was published in 2015 by Fabio Falchi and colleagues, and then close to the main road. So imagining if you're not an expert, not a specialist, but you want this experience, you want to have some amenities and not be completely out in the willy wax to take some special picture. Whereas specialists, and we interviewed a few of the photographers who do pictures, like Niels, whose picture opened up this presentation. Close to food and lodging would be important, close to campsites, low artificial light, but away from the main road, but close to trails. So a place you could hike out to and get like the absolute most pristine sky that you could. So low artificial night sky brightness. So the night sky brightness weights more in this model than in this model, right? So it's 60% here and 40% here. amenities are more important here, amenities are less important there. So these are two models to be just to be able to try to like highlight. So you're here, you want to go do something. Where should you be going? Where can we start sending people that maximize their benefits? The darkest skies, but close to the amenities they need. So this is the sort of tourist or the model of it. The closer you are to Sun Valley and Ketchum, you do have the light dome there. It is a worse sky there, but these dark green spots indicate campsites, things close to the main road, and really anywhere. If you drive up this, I think it's 75 through the middle, you're going to get absolutely incredible skies. And if you've got a clear night. And so this is sort of highlighting that. And the next step that the students are taking, reaching out to hotels and things to see if there's interest in putting together tourism packages, sort of a night sky special during the new moon, during the season when the sun maybe goes down a little bit earlier, so not the middle of the summer, but spring, fall, sometimes when you really could exploit this to get people out and appreciate this resource. And then here's the that's the wrong title on there. We'll fix that next time around. This is in the middle, specialist. This is the specialist model, and it really identifies the places that have a more degraded night sky. And that's relative speaking. This is an incredible night sky, but relatively speaking, if you get up here, you're close to the Thompson Creek mine, and it starts to show up. That's what's showing up here. That's really explicitly coming from that, right around Stanley, and then Sun Valley Ketchum. As good a job as they're doing, it's just not as dark as what you can get out here in some other places. If you're really looking to experience that, as near to a pristine sky as you can get. Now, of course, I recognize we have no pristine skies anymore, and Starlink and other, fleets of satellites are doing this in even faster than we might have imagined. I think this is it's a crime against humanity. Basically, it's stealing the sky from us all, without ever asking anybody whether it was okay, and not even trying to get permission ahead of time from the people who it affects the most. But that's where we are. These are the battles that we all have to fight. So out of this, we recommend, of course, that they go back and update the analysis using the remote sensing, that we have some hemispherical monitoring points, in addition to the ones that we've done to sort of look at annually, track these policies, update the data, and give feedback. Because this is, in a sense, this is a biofeedback thing. It's like you have a policy. How's your town doing? It'd be exciting to see that every year and have the scores come in and know what things are doing, and use these measurement successes and recreational opportunities, tourism opportunities, to do outreach to the public about light pollution, and as a gateway, as I've been discussing with Professor Jackson, as a gateway to STEM outreach as well. And this is what the reserve is all about, and why I've been so excited to lead this group. And to be able to do this work in Central Idaho with the people who are so committed to this issue, and committed to making it work in the long run, be sustainable in the long run. So with thanks to these are the 5 who spent their spring break heading up to Idaho, little road trip. There's 3 more students beyond that who part of the group but didn't make the trip. I really want to, as I said, this has been student work. It's my honor to present their work to you, and I'm happy to take some questions there. This is what it looks like on the bottom right here if you take one of those images under a moon. So that's an extended exposure with a hemispherical lens with the moon in the sky. You can see some stars. There's a Big Dipper right there. You just can't get the amount of data out of it is when you do it with the moon down. It doesn't really help. So that's where we are, and I thank you and love to take questions.
Well, that was really fascinating. Yeah, some really good questions here. One of our guests asks, how willing have LED manufacturers been to limit their spectrum? Is there any engagement with industry to kind of address some of these light pollution issues?
Well, there was a technological reason that they started heavy blue, and that was that the first economically feasible ones were with a blue pump, a blue LED with a phosphor over it that then radiated the light. And the economics of it didn't pencil out, but people were pushing from the start, from the the night sky slash wildlife slash human health community to pushing for lower color temperatures. And the industry has responded, and I would say some more than others. And some really have seen the niche to do wildlife and dark sky friendly lighting to be able to replace the old high pressure, low pressure sodium, even around observatories. So there are manufacturers who have developed filters explicitly for that purpose that only cut maybe 5% of the energy. And so you take a little bit of cut in your efficiency, but you're already saving a bunch of money by going to an LED. A little 5% isn't the big deal that one would imagine it would be, which is good. So there's that. There's filtered LEDs. You can get now off the shelf down to 2700 Kelvin, which is better than 4200 Kelvin, which is say where the city of Los Angeles started out. You can now get PC amber. You can get things down at 22,000 Kelvin, sometimes even lower than that. And so I think as the market is developed for it, the manufacturers are doing it. There is, however, I will say, there's still a lot of people just selling lights with the argument that you have to have full spectrum to see the color for this purpose or that purpose, that for somehow we dealt with high pressure sodium at 1900 Kelvin for basically 60 years and we were all pretty much fine. But now magically to be safe, we have to have full spectrum. And that's where the research is going to have to go. And my goal there is to work with people in that field. So I have a collaborative project right now with some folks at Virginia Tech who work on transportation safety and lighting. And we flat up acknowledge we've got these sort of conflicting things between wildlife and safety. Can you see an obstruction on the road versus or astronomical impacts and safety, and trying to work out what the solutions are to that. And I'm just optimistic that if we all just keep pushing, the industry will follow.
Yeah, that's really fascinating. I'm going to give the students in the room a chance to ask any questions. Do you have any questions? No questions from the room?
Yeah. Can I ask one?
Yeah, please do.
So Travis, you mentioned that there are some cities that have these mandates. Can you talk a little bit about how, like, what can motivate mandates and how they are applied, and or what those mandates are like?
Yeah. So there have been light pollution ordinances for a long time, and the earliest ones arose around observatories, where their economies, places like Flagstaff and Tucson, where their economies really depend on partially on those observatories remaining viable as optical observation sites. And so they involve various types of restrictions that have to do with, sometimes it's by the total amount of light you can have per acre. It can be whether it is shielded, how much light you can emit above 90 degrees, or even sometimes from 80 to 90 degrees. The color temperature of the light, a number of the ordinances in central Idaho now limit outdoor lighting to 3000 Kelvin or 2700 Kelvin. You can have security lighting, but there are often, you can add things about duration that lights can be on. But they all have arisen basically from local initiatives, planning councils, city councils, recognizing the need and then taking action and creating ordinances. And the International Dark Sky Association is a great resource to go to find these things compiled and examples of sort of the model approaches that you might have. And of course, there's all manner of things about enforcement. How do you deal with holiday lights? How do you deal with non-compliance? And one big change that happened a few years back was the American Medical Association, led by a doctor who was an amateur astronomer, came out with a statement about 3000 Kelvin being the maximum outdoor lighting that you should have because of the potential risks to human health and wildlife, et cetera. I consulted to them on that statement as well. And the reason that they picked 3000 Kelvin was at the time, it was the lowest color temperature they could get that was economically viable. and that's why it says maximum 3000 Kelvin. So that's where it comes from. And it can also arise from planning process. Like Salt Lake City right now is doing a big streetlight master plan. And that arose because they started converting their lights to LEDs that were high color temperature, and people got upset. So they put a pause on it, and they said, let's bring in some consultants. And I was one of them. I work for a lighting engineering. It was a sub to a lighting engineering firm. And we kind of looked at the whole situation, the dark sky issues, the nearby dark sky park, the human issues, the wildlife issues, we talked to the police, talked to the fire, talked to, every council district, and eventually you can come to some conclusions about how to get the right amount of light where it needs to be for people for safety, and minimize all these other things through various strategies, brightness, directionality, timing, spectrum, and then basically, do you light or do you not light?
So follow up on that. So why is yellower LED lights more expensive? Is it just there's no incentive to produce more of them, or is it technically more difficult to produce?
So it used to be that there was a pretty technically there used to be a difference between the effectiveness, the efficiency of a 2700 Kelvin, so like an incandescent LED, and a 5000 Kelvin, and it was a significant differential. And when around that time, I was given a talk to the Illuminating Engineering Society in North America and their street and area lighting conference, and I'm like, I know this differential is here, but look toward doing this right, and let's push it because the technology is going to get better. And so where it might used to be 20-30% difference because of technological constraints, through the development of LEDs technologically, it has gotten so that there's maybe a 5% difference or less, or even sometimes comparable, depending on the optics and who's making it and all this sort of thing. You can get equal light output from a 2700 K LED now as as a 4000 K LED. So there's really no reason not to. Now, it is still less efficient to go all the way down to PC amber, the 2000 Kelvin, basically somewhere in that neighborhood, 19 to 22. But just to give an example, this is going to change. I got a call. It was pre-pandemic, so at least a year and a half ago, from people doing research at one of the national labs, and they're like, "We're going to develop a native yellow LED, meaning that there doesn't have to be a phosphor on it or anything. It's just going to be straight yellow LED. It's going to be highly efficient, maybe 10 times more efficient than how we get yellow now." And they're like, "Do you think there'll be a market for it?" I'm like, "Are you completely kidding me?" Yes, of course there's going to be a market for it. We would love that. And because then if you had that and a white, you could even do dynamic lighting, because LEDs, you can turn them up and down just by giving more or less energy. You could have half of them be yellow, half of them be white. During times of the night when you wanted a little more, full spectrum, you would crank up the white with the yellow. And then say after 11 o'clock or something, you turn the whites off, you're just left with a yellow light. And so there's all sorts of flexibility that you can have with LEDs that weren't available in previous technologies. And this is one of the reasons that I have colleagues in the biological sort of world that just say, "Oh, LEDs are horrible. We hate LEDs." I'm like, no. That they're coming whether you like it or not. And B, there are so many things that we can do if we work with the technology that weren't possible before that save energy. We're more likely to get win-win-win solutions with them than we are trying to stick with old technologies.
And then maybe one more question we have. Can you say something about the effects of light pollution on human biological functions? Clearly, there's some connection.
Sure. So the basic thing, like, does light at night affect you? Things like that is probably and the lights in your house, probably your biggest exposure to light at night. But That said, we take those things on voluntarily, and outdoor lighting is, you have generally no control over it. And if we look at the epidemiological evidence, there is a highly significant, through many studies, relationship between well, actually artificial night sky brightness, or proxy for light pollution outdoors, and a whole suite of human health outcomes. They include the couple of the hormonal cancers, so breast cancer and prostate cancer, diabetes, sleep disruption in general, use of sleep medicines. And at the epidemiological level, this signal is very solid, and it shows up even when you account for all the things that you might think be co-founding: air pollution, noise pollution, socioeconomic status, et cetera. Now, socioeconomics does matter in that the impact in the most recent study I saw on sleep was greater in poorer communities, which I imagine has something to do with, if your landlord didn't buy you blackout shades, you're not sleeping in the dark. And crowding, because people are sleeping in rooms that are not necessarily originally intended as bedrooms and maybe don't have shades and whatnot. And in communities that their first priority isn't going to be buying blackout shades so they can, protect their circadian rhythms because of expense. There's mechanistic reasons that we understand how some of these health impacts might be happening. But there's not yet, nor would it be very easy to get, sort of smoking gun evidence that outdoor light at night has a specific human health consequence. We can find the correlation, but the actual smoking gun is kind of like, it's always going to be epidemiological. And so it leads you to needing to make no regrets kind of decisions based on the best evidence that you have. But yes, there are all these things. But then we also can control ourselves, our light exposure ourselves indoors at night. But I do believe, and I've been measuring, I've got a lux logger in the window here to sort of start to monitor how much, in an LA context, what is the actual range of illumination that's hitting a bedroom window at night? And how does that vary relative to sleep? These are forefronts for advancement in study.
Yeah, it's fascinating. And maybe one more question here. How much work do you do with countries like Namibia who are marketing their dark sky reserves as tourism destinations? Are you doing consulting with those folks?
Haven't had that. We did bring in the class, the students connected up with someone who's doing astrotourism in Australia. And we had a nice Zoom call there, and very much the same sort of issues. I've also, other connection I've had was with someone who was going to sell LED lights as a sort of a B Corp kind of thing for social benefit. And her model is sell lights and then donate a light, because she had grown up in a place in an underdeveloped country where she didn't have light to do her homework by, was under literally candles, and thought that providing LED lights, low consumption, or even lanterns and whatnot, was a human development initiative, which it is. But when I consulted to her a little bit, and I said, well, let's make sure that we choose those lights so that you can do the task, but you minimize insect attraction. Because I did a whole study on how to minimize insect attraction with light that's full spectrum, for the explicit purpose of reducing exposure to disease vectors in tropical countries that don't use glass windows and screens, right? And there's quite a few of those things around the world. And so there's two sides of the light coin here. One is light is an indicator of sort of human development and progress and access to opportunity. And we can make sure that we do it right for the number of reasons that both the astronomical is important as well, but the human health reasons to not exacerbate exposure to disease vectors. So I have gotten that when that research ran, it was like 2015, I did get some letters from Africa saying we're interested in this kind of technology, and we have put filters over our flashlights so that we don't attract so many insects at night and things like that.
Wow, I would never have thought about that. That's really important. Well, that was great. Well, thanks so much, Dr. Longcore. That was really fascinating. Stick around for just a second. Folks, thanks for attending tonight. As always, we'll have one of these on the first Friday of every month, all the way through the summer. And I'm going to turn it over to Heidi to talk about next month's talk.
So next month we will have Dr. Yi-Kwan Cheng from the Ohio State University, and he will be talking about how dark is the universe. Just like today, we learned our sky is not dark. It turns out that our universe is not totally dark either. There are photons flying everywhere, and Dr. Cheng is going to talk about how we learn, what kind of astrophysics we can learn from those lights. So we are looking forward to that.
Great. Well, thanks, everyone. Have a good weekend. Get out and enjoy some of this really beautiful